Section 8.6, we're going to take a look at exponential decay functions. So yesterday we looked at exponential growth, where things are getting bigger at a very high rate, and today we're going to look at exponential decay, where things are getting smaller at a very high rate. Okay, and so at the end of the lesson, the hope is that you'll be able to successfully write and graph exponential decay functions, and then tomorrow we're going to dive more into applications of exponential growth and exponential decay functions. Okay, so this was just a quick review from yesterday. Okay, exponential growth functions have the form of y equals ab to the x, where a is bigger than 0 and b is bigger than 1. Okay, now you're going to see how exponential decay is slightly different. Exponential decay still has the form of y equals ab to the x. Your a value is still bigger than 0, but your b value now is between 0 and 1. So in other words, this b value here, whoops, sorry about that. This b value is going to be just some decimal, something between 0 and 1, or a fraction. Okay, and again, that's going to force your graph to get smaller as x gets bigger. Okay, and again, you see the graph here and how that's different. And so the first thing we have to be able to do is graph the function y equals 1/2 x, identify domain and range. And so this is a pretty basic plug and chug. So 1/2 to the -2. Okay, I'm going to do one thing up here. I don't have enough room on the page here, unfortunately, to do a whole lot of work, but I'm going to do what I can here. Remember, we have 1/2 to the -2, so we have 1/2 raised to the -2nd. Remember, this -2, I apologize, not really sure why it's not showing up over there. So anyway, -2 is the exponent up here. Okay, this -2 goes to both guys inside. And so essentially what you end up with is 1 to the -2nd over 2 to the -2nd. And remember, if something's negative, you want to make it positive, you got to move it from top to bottom or bottom to top. So this 1 gets moved to the bottom, this 2 to the -2 gets moved to the top. And so really what we end up with is 2 squared, and we all know 2 squared is just 4. Okay, 1/2 to the -1 is just going to be 2. 1/2 to the 0 is 1. 1/2 to the 1 is obviously just going to be 1/2, and 1/2 squared is 1/4. Okay, so when x is -2, y is 4. 1, 2, 3, 4. When x is -1, y is +2. When x is 0, y is 1. When x is 1, y is 1/2. And when x is 2, y is 1/4. And so the graph of this function looks something like, I'm going to do the best I can here, something like this, where we get extremely small at a pretty high rate. Okay, the domain, again, x values. Is there any restriction on the graph going from left to right? The answer to that question is no. This arrow here indicates that it's going to continue going to the right, and this arrow here indicates it's going to continue going up and left for as far as we can see. So the domain is all real numbers. There's no number, there's no x value that this function cannot be. Now when you look at your range, we're looking at the y value. We ask ourselves, is there a restriction on how far up or down this graph is going to go? Well, again, this arrow indicates this thing's going to keep going in this direction as far as we can see. However, this arrow indicates that we're going to continue going to the right, but we're not necessarily going to keep going down. And in fact, we're going to only be able to go as close as possible to the y-axis, but we're never going to hit it. Okay, and so your range is going to be all y values that are greater than 0. You can never be 0. There's no value of x that you could plug into that function that will spit out a y value of 0. Okay, so your y will always be greater than 0. We're going to get extremely, extremely close to 0, but we'll never actually be 0. Okay, so again, this is probably a good time for you, if you feel confident in this, to go ahead and pause the video and fill out this table of values and see what you get, and try to graph both of these on your own. If not, that's fine too. Just keep plugging away here. So I get -2. When x is -2, then this value is 4. We've already done this one. This is 2. This is 1. We have 1/2, and we have 1/4. Okay, now we throw this -2 way out in front. So in other words, all I have to do now is take all of these values and multiply them by -2 to figure out what goes in that next column. So 4 times -2 is -8. 2 times -2 is -4. 1 times -2 is -2. You get the idea here. That's going to be -1, and -1/4 times -2 is going to be -1/2. And so I'm going to graph these two things on the same axes. So let's see here. -2, 1, 2, 3, 4. So I'm graphing the first one right now, and then I got to go down to 2, and then I go down to 0, and then I'm at 1/2, and then I'm at 1/4. And so again, we said this graph looks something like this. All right, pretty close. And then the second graph says that when x is -2, y is -8. So let's see here. We have a negative, 1, 2, down 1, 2, 3, 4, 5. We're going to go actually way down here off the page somewhere. And then I have when x is -1, y is -4. So -1, 1, 2, 3, 4. And when x is 0, y is -2. And we're going to keep plugging along when x is 1, y is -1. And when x is 2, y is -1/2. Okay, so this graph is going to look something like this. I apologize for that. Obviously, I missed the mark on those two, but that's all right. Okay, you're getting the idea here. And so that's how those two graphs are going to look. This negative sign takes it and flips it onto the bottom. Okay, and then this 2 just tells us that this thing is going to be much steeper. Okay, it's going to be much steeper. It's going to get up towards that x-axis much quicker. Okay, all right. Tell whether the equation represents exponential growth or exponential decay. Again, the only thing you're looking for now is this guy here. What is being raised to a power? Okay, 4, that's bigger than 1. This is growth. Okay, I look at my b here, the thing that's being raised to the x. That's between 0 and 1. This is decay. Go ahead and pause the video. Do part C and D real quick to make sure that you have this. Part C. That's also decay. 2/7 is less than 1. And the last one, part D here, is going to be growth because 5 is bigger than 1. Okay, so hopefully you're getting the idea that growth and decay are very similar. The only difference is your b value, really. Okay, and that's it. Tell whether the table represents an exponential function. If so, write a rule for the function. So again, we're going to look at our common multiplier. So you'll notice I'm increasing by 1 each time. Okay, so that's important to note. And then I ask myself to go from 10 to 100. What do you do? Well, I multiply by 1/10. To go from 10 to 1, what do you multiply by? 1/10. To go from 1 to 1/10, multiply by 1/10. So your common multiplier here is 1/10. And remember, exponential decay is y equals a times b to the x. The b is the common multiplier, so I already know my b is 1/10. And your a is the value of the function when x is 0. So when x is 0, y is just 1. I can put a 1 out front. I don't really need to. So the equation there is just going to be y equals 1/10 to the x power. In part B here, again, I would encourage you to pause the video and see if you're good here. But again, note, right, +1, +1, +1. And then I ask myself to go from 2 to 4 times 4. 8 to 32 times 4. 32 to 128 times 4. All right, so then I go back and I say, all right, well, y equals a times b to the x. All right, and so y equals, remember, a is the value of y when x is 0, so a is 8 here, times your b value is your common multiplier. My common multiplier here is 4 to the x value, to the x power. And so the equation there of that function would be y equals 8 times 4 to the x. Okay, so again, just something for you to take a look at, and hopefully this exponential growth versus exponential decay starts to make a little bit more sense, especially as we look to apply these concepts more in class tomorrow. Okay. Okay, we're going to take a look at this actually in tomorrow night's video. So that's kind of just a quick rundown of what exponential decay is and what the functions look like and how to identify if something is an exponential decay function. And then, as I said, tomorrow's video will deal more with applying exponential growth and decay to various situations.